Okay, so that was the substitution rule for indefinite intervals. Let's look at the substitution rule for definite intervals. All right, so it starts off the same. We're going to be dealing with some kind of composition of functions. Our u substitution will be the inside function. And the definite integral has our limits of integration. All right, so that's what's different so far. Okay, and so when we use our substitution rule, just as before, it will be f of u du, but now the limits of integration, notice if x would used to be a and b used to be, let me say that one more time, x would be a and then x would be b. Those are your limits of integration. But we made the substitution rule. We said u was g of x. And so now x is a and x is b. So our limits of integration are going to turn into g of a and g of b. Okay, let's look at an example. So we're going to find the integral from 0 to 1 of 3t minus 1 to the 50th dt. Okay, and the composition function, the inside function, I would start with 3t minus 1. And then du is just 3 dt. And we just have to substitute for a dt. So let's get dt all by itself by dividing by 3. And now we're ready to make our substitutions. So we go 0 to 1. We said 3t minus 1 was u. And dt was 1/3 du. Okay, and so now we have everything in terms of u, but this 0 and this 1 was for what t was. So I'm going to erase that. And what we're going to do instead is let's go back up to 3t minus 1. Well, when we plug in a 0, 3t minus 1 becomes negative 1. So the lower limit of integration is going to be negative 1. And then if we plug in a 1 for t, the new u will be 3 minus 1, which is 2. So now the new limits of integration are negative 1 to 2. Okay, and now everything is in terms of u, even the limits of integration. All right, so I'm going to move that 1/3 to the outside, this one right here. And let's take this integral. All right, so let's add 1 to the exponent and then 1 over the exponent. And now we are going to evaluate that from 2 to negative 1. All right, and if you want to, you can move the 1 over 50 first, since it's just a constant factor to the outside. And it makes it a little bit easier to evaluate u to the 51 from negative 1 to 2. Or you can just leave the fraction in there as well. All right, 3 times 51 is 153. And now we're going to plug in 2. And we're going to subtract what happens when we plug in negative 1. Notice parentheses are important, especially when working with negative numbers. All right, 2 over 51. Do I have my calculator? I don't. But I have a feeling that might overload your calculator. Your calculator is only so powerful. So don't worry about multiplying that through. we can just write out 2 to the 51st. And then what about negative 1 to the 51st? What's that going to be? It's just going to be negative 1, right? So minus negative 1 will be plus 1. And we can just leave our solution like that. And notice, because it's a definite integral, we do not need the plus c. We only need plus c to define a family of functions for indefinite integrals. Okay, so let me stick with this example. And I'm just going to write an alternative method, because we all like to view or approach problems in different ways. So some people like to do the limits of integration after resubstituting. So for instance, they would come at this point, so the integral of u to the 50th times 1/3 du. All right, so they would pick up here, and they would not write the limits of integration. Okay, so for instance, they would do like 1/3. The integral of u to the 50 is this. We've discussed that already. And then at this point, the danger of this is forgetting to resubstitute. But at this point, we resubstitute. We do not have to do that in the example above, which is why I prefer using this method. But let's see, u was 3t minus 1. Because if we use the top method, the benefit of that is once we substitute everything that needs to be substituted, we just work it out without a second thought, which is normal. But here you have to remember to resubstitute. And then after you resubstitute, then you do your original integration. Okay, so it's a preference, right? However, I recommend committing to one method. Once you start going back and forth, that's when you make mistakes. Okay, and we end up with the same solution. Okay, which is, 2 to the, I'll just write it out. All right, but please just choose one method. Either you don't worry about the limits of integration till the end after you substitute, or you take care of everything in the first step and finish the problem without having to substitute. And again, I prefer this method, so this is the method I'm going to be demonstrating. But if you like the alternative method, use it. We just should all end up in the same spot. Okay, so let's look at another example. And you guys can try this on your own. So you have all the tools you need. You might have to combine some tools, but that's what math is. Sometimes we have to combine ideas, and we can do that. So push pause, and then let's see how you guys do. All right, so I see a composition of functions in the bottom, the square root of 1 plus 2x. So I'm going to say that 1 plus 2x could potentially be my inside function. Remember, sometimes it's a guessing game. We go down one path, it doesn't work. We have to go down another path. Okay, so there we go. So what have we taken care of? We took care of this. That's going to become u. Dx will become 1/2 du. And now we're left with x. So what can we do? Well, we saw an example like this. Here's an x right here. So let's just solve it in terms of u. Okay? So we can subtract 1 and divide by 2. All right, and then that will take care of this x up on top. Okay, lovely. So let's talk about the limits of integration. What color? I'll do that in space color. So let's do u of 0. U of 0 is going to be 1 plus 0 is 1. And when x is equal to 4, again, I'm just using that formula. And then when x is 4, 2 times 4 is 8, plus 1 is 9. All right, so let's go ahead and substitute everything we know. So the new limits of integration, we're going to say 0 to 4 turned out to be 1 to 9. Okay, and what else? So the bottom, 1 plus 2x, 1 plus 2x became u, and dx became 1/2 du. And then we had to rinse, wash, and repeat, and x is u minus 1 over 2. So look at all that substitution. Isn't that wild? Okay, so let's clean it up. So I see 2 1/2s here, right? This is a 1/2. Dividing by 2 is like 1/2. Here's another 1/2. So I'm going to pull out, since they're factors, I can do it. I can pull out 1/2 times 1/2. What's that going to be? 1/4. So I pulled out the 1/2. I pulled out the other 1/2. 1/2 times 1/2 is 1/4. All right, so we're left with u minus 1 in the top over the square root of u times du. Okay, so we're almost ready to go. So in this case, you know, this doesn't look like any any derivative that I can think of. So we had a technique when you have a numerator and it's just divided by a single term in the denominator. Let's break up that fraction. So u over root u, I'm going to write it like this. All right, and this. Now we're getting somewhere. We're getting to something that we can take the integral of. So let's see, this is going to be u to the 1/2 minus u to the negative 1/2. Okay, so let's take that integral. All right, so we're looking at, let's add 1, so 3/2. And we have the 2/3 then as our new coefficient. Adding 1 here will become positive 1/2. The coefficient is the reciprocal. And we're going to evaluate that from 1 to 9. Now remember, 1 and 9 isn't, these are u's, right? This is what u is. Before, 0 and 4 was what x is. But we already did the hard work, so we can just keep going. We don't have to worry about substituting. So let's see. We can't really make our life easier because there's no constant we can factor out. So this whole expression has to be evaluated from 1 to 9. And we're worried about the 1/4 at the end. All right, so let's plug in the 9 first. And then we'll plug in the 1. Okay, let's keep going. It's so long, right? Okay, so 9 to the 3/2. So first I would take the square root. That's what the denominator 2 tells me. So that will be 3. And then 3 cubed is, 27. But then I have an extra copy of 3. So 27 divided by 3 is 9. So we're going to be looking at 2 times 9. That's how that simplifies. And then 9 to the 1/2 is 3. And then minus, let's see, we have, these are both just going to be 1. 1 and 1. So minus 2/3 minus negative 2, which will be plus 2. Okay, so we're looking at 1/4 times 18 minus 6 minus 2/3 plus 2. Okay, so here we go. 18 minus 6 is 12, plus 2 is 14. Okay, and then what else? Well, I guess we can make a common denominator. Let's multiply 3 to that 14 top and bottom. So 42 over 3 minus 2/3 is 40 over 3. And we're almost done. We have some nice cancellation. And so what do we end up with? We got 10/3. Good. All right. So excellent. So that was a lot in that problem, right? That was some really great review of fractional exponents and PEMDAS and just kind of your nice basic arithmetic stuff. So there you go. So the last thing we're going to deal with in this section is talking about even and odd functions, because even and odd functions are called that because they have this nice symmetry. And we can use that to make our life easier. And we'll explain how. So for even functions, do you remember how to tell if a function's even? There's a test. Well, there's a test. It's always the same for symmetry. You plug in -x. And for an even function, when you plug in -x, you get back the same function. And the symmetry is along the y-axis. All right, so a really basic even function would just be something like x squared. And it's symmetrical about the y-axis, right? And so what we're going to be looking at on these even functions, we're going to be concerned about taking areas from A to A, okay? And when I say area, I meant to say integral. And I kind of got that off, but that's okay. It'll be approximated. So what we have when a function is even, then when we take the integral from -a to a of that function, remember that's the area under the curve, the net area. Well, because we have this nice symmetry, this area on the right is the same as this area on the left, right? Because we're going from -a to a. So we can just look at twice the integral from 0 to a. Okay, so that can help us figuring out these complicated integrals. So what else? Let's talk about odd functions. So odd functions, again, the test is the same. We plug in -x. And when we plug in -x, we get back the opposite of the function. And in that case, the function is symmetric about the origin. All right. So let's see, x cubed is an odd function, but I'm going to use our favorite odd function, which is the sine. Everyone loves the sine function, right? Okay, so in this case, let's do the same thing. So this is what it means to be symmetric about the origin. Essentially, it's a reflection across the x-axis, and then it's a reflection across the y-axis. Okay, so notice the point xy up here becomes -x, -y down below. And if we want to do the same thing up here, xy becomes, let's see, the x is -x, but then the y is the same. So fun, right? Okay, so let's say we have a spot, and we'll just use this. We'll go -a to a, right? This nice symmetry. And so we would be looking at, if we were to take the integral, it would be this area plus this area. And what do you think we can say about these two areas? They're the same quantity because of the symmetry, but they differ in sign. So what happens from the integral from negative a to a of these odd symmetric functions? Well, it's the net area. So what's negative a plus a? What's it, like negative 5 plus 5? 0. So if f is odd, then taking the integral from negative a to a of a function is just 0. Isn't that nice? Okay, so let's see how this can help us. Let's say we're taking the integral from negative pi over 3 to pi over 3. All right, so this is our first kind of red flag or clue. They're opposite, right? So negative a to a. And then we have x to the 4th sine of x dx. And we're looking at this, and I can't think of a substitution to make, right? There is no u substitution, nor is there a function whose derivative is x to the 4th sine of x. Or if there is a function, I don't know how to find it. So what can we do? We look like we're a little bit stuck. So that's why realizing that this is like a negative a to a situation is important. So let's see what happens when we plug in negative x. So negative x to the 4th sine of negative x. Okay, well, negative x to the 4th is going to become positive. Sine is an odd function, so when we plug in negative x, we have a property that tells us that's the same as negative sine. So we're looking at negative, bring the negative out front, sine of x, which is the opposite of the original function. Right? The original function was x to the 4th sine x, and now we have a minus sign in front of it. So we just showed that f of negative x is negative f of x. So this function is odd. So by this little theorem we have, that means if we're looking at negative pi over 3 to pi over 3 of an odd function, guess what that integral is going to equal? 0. All right, so we can use the fact whether it's even or odd as another way to figure out these integrals.